Hello, my name is Chen, and today I'll be talking about Physics 2211, Lab 3, black hole. To start off with, we'll want to analyze the orbital motion of a star in a system where the center includes a black hole. We then use the star's motion to estimate the force applied on it, and our goal is to use this information to find the mass of the black hole. In the first part, we want to analytically use data from the model to calculate the net force on the star, and then the mass of the black hole from the formula of gravitational force. In the second part, we want to find the escape velocity so our ship can navigate out the system that includes both forces from the planets that we landed on and the black hole situated at the center of the system. These are the equations and physics principles that we're going to use, which includes the momentum principle, the formula for escape velocity, which we'll use in the second part, and the gravitational force, which we'll use in the first part to find the mass of a black hole. These are the initial conditions for part one. The mass of the black hole is what we're trying to find. Mass of the star, delta T, which is a day or approximately 86,000 seconds. Position of the black hole, it's at the center, so it's at 0, 0, 0, and the gravitational constant. So now we can go through the code for part one. As you can see, start off with, I found the velocity vectors by going through the xval array, and then we'll compute the momentum vectors, initial and final momentum vectors by time, because momentum just equals mass times velocity, and then we'll use this and delta v and delta p to find dp dt. And then using Newton's second law, we know that net force is just equal to change in momentum. And then we need to calculate both the parallel portion and the perpendicular portion of the change in momentum here, and then we set those two, which is equal to F net parallel and then F net perpendicular. Next, we find the mass of the black hole by simply singling out the mass variable of one of the entities into the left side of the equation, as you can see here. So this is just another rearranged version of the gravitational formula. And since for each iteration we find a different prediction for the mass of the black hole, what I did is I added the predicted mass of this iteration to this variable, and then in the end we just divide it by the number of times this loop has run, so we get an average estimate of the mass of the black hole. So this is the results we got for part one. This is F net parallel, F net perpendicular, and the mass of the black hole. So now we'll use the mass of the black hole that we found in part one and plug into part two. And here you have the mass of the planet, mass of the ship, gravitational constant, and delta T. So now I can look through the code for part two. So we start off with by finding the net force of the black hole and the net force of the planet on the ship. And then we add these two, we just get the net force on the ship. And then we find the the force of the black hole on the planet, force of the ship on the planet. We add those two and we get the net force on the planet. And we use these two and use Newton's second law to update both the planet's velocity and position and the ship's velocity and position. And so what I did is to find a initial velocity, I used the formula for escape velocity. And by plugging in both the mass of the black hole and the mass of the planet, we get the escape velocity for these two entities. And by adding them up, we get this number, which is what I use for our initial guess as our starting velocity to escape the system. And luckily, we didn't crash into the black hole or the planet. So other sources of errors and improvements: smaller time increments to update the position of velocity, and we're also only concerned about the three entities, where in real life there's probably a lot more factors that goes into the system, includes systems that have multiple planets or stars, and heat will also be a factor as well, and a lot of other unknowns. So what does it mean? Net force versus rate of change of momentum. Although the parallel and perpendicular components of dp dt and F net are the same numerically, conceptually they are not the same. The momentum principle connects them, but they're not the same in how they're found. So net force is found by summing the forces on the system, while change in momentum is found by analyzing the system's motion. So if we know the net force, we can update the momentum based on the net force. If the momentum is changing, we know that there is a net force on the system. And the momentum principle says that if there's not a net force, if there is a net force and there's a change in momentum, so conceptually they're not the same. So what if we're trying to orbit around the black hole? Since now we want to orbit around the black hole, this means that the perpendicular component of the net force should be 0, and this also means that there's a force that offsets the black hole's gravitational force in the perpendicular direction. So the initial velocity needs to be in the opposite direction of the black hole's gravitational force, and the magnitude should be equal greater than the black hole's gravitational force.